Showtime!
Ladies and gentlemen, please make your way to your seats.
Showtime!
Please make your way to your seats. The show is about to begin.
Showtime!
Let the magic begin.
So I saw an interview with Elon Musk not too long ago saying that we are at solar panel maximum efficiency we're going to get out of solar panels. And then I see this. New solar cell design offers over 90% efficiency, boost durability. So what are we talking about here?
Yeah, so this is straight out of Morocco. They've developed an innovative new design for photovoltaic-thermal solar panels. Apparently, it achieves a remarkable efficiency level of over 90%. And I think currently they're, 30%, 40? Or I think 30 at the most. So their approach, it's creative. It involves a customized channel box heat exchanger that ensures the surface of the panel has direct contact with a cooling fluid, which promotes enhanced heat transfer and addresses the problem of uneven temperatures that degrade performance in conventional photovoltaic thermal panels. The key to the new design is the heat exchanger. It's made of aluminum, which attaches directly to the photovoltaic module. It features dedicated channels for the inlet and outlet of the cooling fluid, as well as this specific plate in the heat exchange zone to optimize heat transfer between the panel and the fluid. So water flows through the exchanger as the cooling medium, and it facilitates a kind of convective heat exchange across the entire panel surface. So in simulations, using specialized software, it indicated it can achieve electrical efficiency of 12.11% and thermal efficiency of 78.59, combining for an exceptional total efficiency approaching 91%. Now, again, we're talking simulations. They also found that the cooling fluid flow rate significantly impacted performance. So for every 10 liter per hour increase, solar cell temperature dropped nearly 34 degrees Fahrenheit. So they did highlight that the panel's good performance in terms of temperature uniformity and overall efficiency, right? The adaptable design apparently can provide air or water heating, making it suitable for integration in sustainable buildings and things like that. So really cool, but again, stimulated cool, if that makes sense.
Yeah, absolutely. I'm looking at this. I took a look at current technology has it at reaching a conversion efficiency rate of 32.24% using perovskite silicon tandem cells, where their silicon solar cells are at 27.3% efficiency for. So this is a huge increase.
Huge jump. Like this is a ridiculous jump. Like this is one of those jumps where you're like, really? Like it's one of those, right?
Yeah, that was my next question is, everything up to this point has been, we're at maximum conversion for this. And all of a sudden something like this jumps forward. What does this mean?
Yeah.
Like, is it real is more of a question.
Exactly. Yeah. Yeah. But again, so as a caveat here, these are simulated environments. So we'll have to see what they achieve when they actually build this. So and test it in the real world. I'm guessing we'll get closer to 70%, which is still double what we currently have. So
it talks about the durability, that it increases the durability and solving durability issues with advanced solar panels. Are these breaking down all the time?
So the article, it suggests that there's, in the article itself, that there's a potential for improved longevity and lower maintenance requirements. So because you're evening out temperatures, the new design kind of reduces thermal stress on components like the solar cells and adhesives. So thermal cycling is a major contributor to solar panel degradation. So keeping the temperatures low also helps prevent warping, delamination of panels that can occur, especially in hot climates. So this damage further reduces working lifespan. The researchers have suggested that their design helps solve the problem of temperature inequality that impacts those panels. This implies it could significantly extend operational lifetimes. So longer lasting panels means system owners would benefit from greater lifetime energy production before needing to replace the panels. And then extended durability also translates to lower lifetime costs, right? By reducing the efficiency of the frequency of repairs, panel replacements, and different things over the system's operational years.
Okay, two things. Well, let's start with how easy is it going to be to manufacture these things?
Yeah, so the article itself didn't provide specific details, but the use of the customized aluminum heat exchanger doesn't really appear to add engineering complexity compared to conventional photovoltaic panels. So the additional component obviously would increase production steps, but the base components like the photovoltaic cells, the EVA layers, the glass cover, they seem like they're similar to traditional panels. So the manufacturing process for those could essentially just translate over. The heat exchanger's channel-based structure may be somewhat challenging, but they could introduce some sort of automated fabrication techniques like extrusion or stamping, which could mitigate some of the added complexities. So the only thing really that might add additional componentry is the aluminum heat exchanger. But again, it's nothing. It's no rocket science kind of design. It's pretty straightforward. It's just a matter of figuring out the manufacturing process.
So how are they going to validate it? How soon are they going to validate it?
Yeah, that's a good question. So the panel, it's currently in the early prototype stage. So they modeled it, they simulated it, and now they're going to have to build the prototype. So next steps will involve physically building the prototypes for lab and outdoor testing, which is probably 1 to 2 years to do robust performance characterization across conditions. Then you can expect probably another 2-3 years for pilot manufacturing trials, work out the fabrication methods and costs, and then another 3-4 years for larger scale trial deployments, optimizing manufacturability, different things like that. So, like, again, I'm guessing as early as 5 years away, but could be, if this doesn't pan out, like maybe 7 to 10.
And do you see that if this testing goes well, that in the next 7 to 10 years, they'll start replacing the current solar panel farms with these?
Honestly, if this technology proves itself, I can see people pouring money into this because, like, this is a game changer for solar energy. Because if we can, even if they get it, like I said, to 70%, that's double what is currently out there, and that's a huge game changer.
It definitely, the article talks about how it works better in high temperatures because it distributes the heat evenly and stuff. But what about low light?
Yeah, so I'm not too sure how the low light will. I'm guessing because of the efficiency, it obviously will work better in any kind of environment. But because of the design of it, it's going to work best in high heat because it works on temperature differentiation, right? So, yeah, given the low light, it's still going to be better, but I don't know how much.
So, what are the drawbacks or trade-offs compared to conventional, or are there any solar panels?
Yeah, so increased complexity. So there's the integrated heat exchanger, which adds engineering complexity. And if we're going to be honest, more points of possible failure. Okay, so they could potentially reduce reliability over time. There's obviously higher costs because of the more components. It is untested. Like these panels that have been around that have slowly increased efficiency, I think they've reached the max based on the current design. They've been around for years. So they've got tested reliability. Well, they as best reliability as you can get. But yeah, so the thing with these panels is the thermal regulation requires fluid. So the heat exchanger will need to continuously flow fluid to maintain the even temperatures. With that, it'll probably be heavier. There's a risk of the fluid freezing. There's the like, again, when we talk about optimal conditions, so performance gains may depend on carefully optimized fluid flow rates. So they're going to have to experiment with all of that.
Indeed, I'm really looking forward to following this and seeing if we're really going to see these big jumps, because, solar hasn't quite got to the level we'd like it to, and this would change everything.
Absolutely. Yeah, this would be a game changer. And let's hope it does, because we need something.
Wow, that was